about a very old-fashioned story on gamma ray astronomy, and this is work that's encapsulated in this paper that came out in July, and this paper that will hopefully come out in the next 2 weeks, with these various people, most of which were once or still are affiliated with Berkeley in some way, the exceptions being Josh Foster at MIT and Yotam at Technion. Okay, so starting from a baseline that where we can all agree, we don't know what dark matter is, and it certainly isn't for lack of trying. We've tried as a community very hard over a very long period of time, and we're not particularly close to coming up with a definitive statement. And over the years, there are guesses of what dark matter could be and the ways that we could potentially look for them have vastly expanded. This story is not about any of those things. This story is about some of our oldest tried and true ideas, specifically the WIMP story, weakly interacting massive particles, which I think you all have heard about. But it is the good year of 2022, and I think it is worth clarifying what I mean by this term, because the meaning of this term has drifted a little bit since its first conception until now. There are a number of things that we can mean by it, roughly separated by things that it is versus things that it does, and I think probably epitomized by our drift in this interpretation of this W. Do I mean electroweak specifically? Do I mean weak scale? Or do I mean just small, not a large interaction? So for the first half of the talk, I'm going to drop the theory prior, the things that it is, and ask you to bear with the things that it does for a little bit. I promise I will pick the theory prior back up. But for now, a WIMP is a thing that quacks like a WIMP, so a thing that you can ostensibly look for in the traditional make-break-shake paradigm. It weighs roughly what you think it weighs, like a order 100 GeV. It annihilates at order picobar scales. That's the picture. Okay, good. So in this very pragmatic picture, the thing that is still attractive about it, I would argue, is this concept of the thermal relic, this idea that gives you a way to link the way that the particle interacts in a particle physics way with the literal only thing we know about it, dark matter as a whole, which is how much we have. This idea of the thermal very compellingly links these two concepts and is the thing that gives us some prior for any of the particle physics properties, at least under this paradigm. And I think the thing that's probably the biggest enemy of this paradigm, at least in the last couple of years, is this very robust direct detection program that has put some a very exquisitely constraining bounds on the way that dark matter can interact. A lot of xenon hasn't seen anything. So the statement is that the modern-day viable WIMP, if it is your job to build such a model, needs the amount of annihilation, which is priored on this thermal relic concept, that is much bigger than the amount of scattering, which is constrained by the amount of direct detection that you see, to the tune of 10 orders of magnitude. That's the assignment. Ultimately, this is not, a very difficult assignment. We'll use this when we need to point at something. And we have inadvertently been training ourselves to do this in the last decade or so. There are a number of ways to do this. I think the most straightforward of which is the cascade annihilation picture. But the idea is that it's easy to do. It's in fact so easy to do that it's a little bit too easy to hide any modern-day WIMP model from direct detection altogether. The upshot of which is that ultimately direct detection is not the right hill to die on if your goal, if the thing that you want to realize is this thermal relic WIMP picture. And the thing where you obviously have a prior on which to expect is this indirect detection predicated on this thermal relic picture.
So can you do previous slide?
Yeah, of course.
This number, can you explain a little bit how this number rise? The 10 to the 10?
Yeah, so this is like there are tildes, but roughly there are strong constraints on what this needs to be, and then this needs to be order picobarn. And,
Okay.
And this is for these masses order like 10 to the negative 10 picobarn.
Okay.
So the denominator is set by the liquid xenon
Yeah.
limits, and
Yeah.
the numerator is a sigma v for annihilation in the early universe as opposed to now?
Yes, exactly.
Okay.
Okay, got it.
Good. Okay, so this is an indirect detection story, the main character of which is this Fermi telescope that I am sure all of you have heard at least some words about. This is a space-based gamma ray telescope, GeV to TeV reach. And the thing I guess to emphasize, it's been collecting data since like August of 2008, and it's still going kind of on like a year-by-year basis. We have a lot of gamma ray data, and kind of the last time we seriously checked in on it was it was like order 7-8 years ago. Most of the indirect detection constraints that particle physicists readily invoke in like most of the model building papers are constraints from like Fermi 2015. So we should check back in on it, see what it can do for us now. We've about doubled the data set. So I'm going to do two things with it. I'm going to do a line search and a continuum search, looking for spinning the story in two separate ways. I think you've heard a little bit of this story a couple weeks ago that Josh Foster might have given you, so I'll hopefully keep the second bit brief and adjust the time as we go. I think I will try to structure this story around the concept of emotional closure. These are things, empirical and theoretical, that have been with us for a while, that we have struggled to converge on a conclusion for both of these things. They're compelling ideas or compelling anomalies that we've struggled so hard to like put an ending on it that it's maybe been a couple years since we've paid attention. So I guess I'm here to remind you that it's still compelling and still worth paying attention to, still worth checking in on. Okay, so first story. This is a line search, and we're going to try to use this to say something about the galactic center axis. Okay, so first off, the galactic center axis. It's exactly what it is on the tin for anyone who happens to have not heard of it. The things to know about it is that it's extremely robust as an excess. We're pretty sure that it exists as an excess. And this excess could be explained by annihilating dark matter, in that it is both spatially and spectrally consistent with pretty much what you would expect for a WIMP-type annihilation. Spectrally consistent to like a order 50 GeV dark matter annihilating to V-type quarks or something of the like, at about exactly the magnitude that you would expect for WIMP-type annihilation, if you assume that the early universe and present day have roughly the same annihilation strengths. And it's spatially consistent with what you would expect a dark matter halo to look like, albeit a little more cuspy at the center. So it's not...
Are you going to explain what you mean by robust with an excess? There's a comparison implied there, right? There's a baseline. Are you going to talk more about that?
It's especially what do you mean by there's
Well, what does that mean that it's, what does it even mean that it's an excess? I'm an outsider for the field, so what does that even mean that it's an excess?
there are significantly more gamma rays there than we expect with our astrophysical models.
Okay, so it's comparison to models, and so the statement that's robust is it's very hard to account for them by tweaking the models.
The models that we have, like you can add an extra astrophysical emission, which is of course what the contending explanation is. But with the things that we currently know that exist that emit gamma rays at these energies, we see significantly more of them than we linear sigma, it's like 70 sigma or something absurd like that. I mean, obviously nothing is 70 sigma, but it's a very large difference between what you see and what you expect.
There was a debate about whether they come from point sources a few years ago. Is that including your, well, sorry, it's access above these point source, or it's even included in point source?
Oh no, of course not. So like one of the other explanations for this excess is astrophysical, that there are these unresolved point sources that are causing this emission. But there is something that is like not in the current model that is causing this excess. Is what the robustness is. You have to propose a thing, and the thing could be like millisecond pulsars, and the thing could be dark matter. Those are, I would say, the main contending explanations. There have been a true litany of work, you know, like developing lots of very sophisticated data analysis strategies, trying to characterize whether this excess is better fit to what you expect for astrophysical emission versus what you expect for dark matter emission. And there is not a lot of convergence on the subject. Like, it seemed like the dark matter explanation was dead for a couple of years, and then it's recently kind of come back in a series of papers with a lot of like Star Wars movie title synergy. But the point is, it's unclear what this excess is from. Like, there is an excess. It's unclear if it's dark matter. Dark matter is a contending explanation, and I think what we have maybe learned for the last decade of trying to understand this by analyzing the excess itself is that it's very hard to reach a conclusion just by analyzing the spectrum of the excess to death. I could be wrong, but it seems at least very difficult to get it from this direction. Okay, so what am I going to try to do with gamma ray lines? So let's set the baseline a little bit. Any amount of dark matter annihilation with a two-body final state, one of which is a photon, will give you a monochromatic photon line. This is just because the dark matter is very non-relativistic in the galaxy. So just by kinematics, you get a definite energy photon, and that's a line. And the point is that photon lines are essentially background free. There is nothing that we know of that gives you a spike in these energies.
There was one line that went away.
Huh?
There was one line that went
There
away.
was one line that went away. Not at these energies, but there was.
Like you're talking about 13 keV line?
No, it was 100 GeV.
There was like a
Fermi
130
data.
GeV
Oh,
line.
yeah.
Yeah.
30
And then there
GeV.
was
One of
a-
your co-authors was.
Yeah, yes, indeed. There's a 130 GeV line, there's like a 3.5 keV line. There are lines, the 3.5 keV line might be like potassium or something like that.
Yeah, I didn't mean KV. There's a lot of X-ray transitions in the KV.
Yeah.
I meant the GV.
Yeah, there was a three.
But there was an instrumental issue
Yeah,
that caused the background, at least at one point in time.
this is true. But it is rare, and if we find a line like this, it is more cause for excitement than finding like a sort of nebulous bump in the spectrum, the way that GCE is. So we are, in principle, much more sensitive to this type of emission. It's easier to search for. In the context of the GCE, any model that you may propose that would cause the galactic center excess, in most cases, there are exceptions, but in most cases, you can do exactly this to them. You can close off the charged fermions because, or whatever final states, most often than not, they're going to be charged into this like triangle loop that radiates off photons. So associated to any amount of annihilation that gives you ostensibly the galactic center excess, there is a corresponding amount of monochromatic gamma rays that you would expect from the same model. This is, of course, very subdominant. You have like WIMP factors, whatever the masses are, so on and so forth, like alpha squared. But it is model by model, like in a lot of models, an irreducible component, and it's very predictive because we have, because if the conceit of your model is that this process is the thing that causes the galactic center excess, you are locked into a mass and a cross-section to a certain extent. That gives you a very specific prediction for what this photon line is, and you need to find it, and if it, and if it's not there, then this is not the correct assumption. And this is much easier to find, even though it's a subdominant component, so that's what we're hoping to do. And so, yeah, so the way I'm selling this is that it's one of the many ways to stress test dark matter interpretations of the galactic center axis. There are a bunch of different ways that people have tried to test these dark matter explanations of the galactic center axis. The notable ones are looking for similar emissions in Milky Way dwarfs, or looking for similar excesses in other tracer particles, antiprotons, positrons, other things that you would expect that would come from dark matter annihilations. And I think in comparison with these different types of probes, the virtue of this method is it kind of like is more of an apples to apples comparison insofar as it's looking for the same particle in the same patch of sky. So we'll be looking at the same patch of sky that produces the galactic center excess, and also looking for gamma rays. So the idea is that like you can't hide behind a different J factor in between the galactic center and Milky Way dwarfs. You can't hide behind like different propagation functions between gamma rays and charged particles, things that would like obfuscate this direct comparison between the galactic center excess and like the lack of an excess in Milky Way dwarfs, for instance. So this is a more like model dependent, like this is a prediction that's very model by model, but you can't hide behind these astrophysical things that would potentially confuse your results. So if you, like for a model, if you find it, then it's there. If you don't find it, then this is not the galactic center axis. Okay, good. We're going to put in a fiducial model. Ye olde Higgs portal dark matter. What I've recently been told is known as the Hooperon or Gooperon, but is one of the first proposed models to explain this dark matter access. It's a simple enough model, Majorana dark matter, coupled to the Higgs does its thing. The one trick I will pull is put in a pseudoscalar coupling to the Higgs. This allows me to keep the annihilation S wave, but suppress the scattering with velocity, and this helps me like achieve the annihilation scattering hierarchy to make it not ruled out. The other nice thing about this Higgs portal is that it comes baked in with an elevated amount of photon line per annihilation ratio, in that for a 50-ish GeV dark matter, which is the prior you should keep in mind for something that explains this excess, the dark matter is going to annihilate to B's mostly, but the things dominantly running in the loops are like W's and T's, things with higher masses, things with larger couplings. So you get essentially an elevated branching ratio to photons. Turns out to be like 10 to the minus 3. It's the Higgs branching ratio to gamma gamma if you had a Higgs that was like 80 GeV or something like that. That's what this number is. But given that you have some sort of prior on what this annihilation cross-section is, you know what the branching ratio is just from the model. This gives you a solid prediction for what the line you're looking for is. Yeah, it's fully a fiducial object just because it's simple and a good fit, and it is advantageous for the thing that I'm trying to sell. Okay, so we're going into the weeds for like how to do this gamma ray analysis for a little bit. We'll come out of it soon, I promise. But the first thing we're going to have to do is obtain a fit for this model to the galactic center axis. We need to establish what that expectation is before we can go looking for the lines. The flux that you expect from dark matter annihilation, the gamma ray flux that you would expect to come out the other end, is split into prompt and secondary components. The prompt emission is just the dark matter, like the gamma ray production from dark matter annihilation in the vacuum. Like the dark matter annihilates to some final states, those final states cascade and like hadronize, decay, and they produce gamma rays, and the gamma rays get to us. That's the prompt contribution. The secondary contribution is from the essentially like electron-positron contributions, electron-positron products of this cascade hadronization process that go and interact with the other stuff in the galaxy and then produce gamma rays. So prompt contribution is from a vacuum. Secondary contribution is the gamma rays that come from interacting with the other stuff in the galaxy. The prompt contribution is kind of exactly what you would expect it to be. It's how much dark matter is in the place you're looking at, how often it annihilates, and the thing you expect per annihilation. Simple enough. The amount of dark matter that is in the place you're looking at is encapsulated by this object called the J factor. Pretty common parlance in this world. But you need to make an assumption about the distribution of dark matter in the galaxy. We take this like generalized NFW approach, which is an empirical fit to these dark matter only large-scale simulations that have been around for a while, where we make an adjustment to this power index in order to fit what we know the galactic center axis morphologically prefers, which is this like slightly contracted NFW.
Sorry, what's the branch ratio chi to XX?
Well, that's model dependent, right? Like it's just for all the final states that this annihilation produces. For instance, for this Higgs portal, like the Bs, and taus,
Oh, yeah.
you sum over all the final states. There's some branching from chi to like your final state of choice, and then there's a different injection spectrum of that final state to gamma rays. There's like a handy Mathematica notebook called the Core Particle Physics cookbook, the PPPC, that essentially gives you a library of all these injection spectra.
Okay.
So yeah, so that's, you sum over all the final states that exist. Good. Okay. The secondary emission is a little scary. Ultimately it becomes the subdominant part of the story, but I felt like I needed to mention it. It's more or less the same thing, except you have to integrate over all of the electron injection that you can expect, and then the electron has to like interact with the stuff in the galaxy, so you have to integrate over like the amount of stuff in the galaxy, how these charged particles propagate, which means you have to model like the galactic field, like the galactic magnetic field. So this, all this scary astrophysics goes in this function, and the same people who've done this PDPC have produced all these like libraries of astrophysical emission. We consider like these two main sources of astrophysical emission, the secondary emission, inverse Compton scattering, and Bremsstrahlung, and like these interaction strengths, how much stuff there is in the galaxy. All of this is encapsulated in this function. It is subject to a lot of different assumptions about what the model of the galaxy is, propagation models, magnetic field, things like that. We marginalize over some of these, and we find that in all cases this is a pretty minor contribution to this model that we care about. This is because the secondary contribution is mainly a pain for final states that are like muons, like leptonic, but also like lighter leptons and muons and electrons, and those are very small branching ratio for this Higgs portal. So we checked it, it doesn't really matter, which is good because there's a lot of uncertainty there. Okay, so this is the spectrum we expect from dark matter. This is the spectrum that we observe. This is the galactic center excess itself. I didn't do the reduction to this excess. I'll credit to to tomorrow in this paper from last year using 11 years of Fermi data and an ROI of 40 by 40 degrees. Essentially, he did the fit of the data with a bunch of astrophysical templates and this like generalized dark matter emission. He modeled the dark matter as like some sort of like paraboloid, log paraboloid object with like free-floating indices to like emulate a range of different dark matter emissions. And this was essentially the signal minus the background that they got.
Have people studied that spectrum as a function of where you look?
A little bit. It is the most concentrated in the galactic center. So this,
No,
yeah.
I mean, if you try to do a template fit that also has the spectrum and extract the spectrum of the excess in different places, is it always the same? I'm not saying that rules out an astrophysical background or anything.
Yeah, so people have specifically done this, specifically in the context of trying to characterize whether it's better fit to an astrophysical background or with the dark matter, because the dark matter is expected to be mostly isotropic, and the pulsars are expected to follow the galactic disk, so they're going to be like slightly boxier. So people have done this. So people have done this template type of analysis. I don't believe the spectrum is very spectrally different across the different parts of the sky. And I think, well, one of the things is they found that this templating approach wasn't very trustworthy. So they did this templating approach and found like a strong preference for the astrophysical explanation, like a stronger fit to the pulsars. But essentially they found that if they artificially injected what they knew was dark matter signal, they also got a strong fit to the pulsars. So I guess the answer is like spectrally, I don't believe it's very different. Like in spatial variation, there have been template approaches done. I don't think they have a very conclusive answer. Okay. But this is averaged over the entire ROI. And we're just using this to get a benchmark cross-section and mass in order to search for. So that's all I want out of it. Someone did the hard work for me, I can just go and do a chi-squared fit. That's all I want to do. Okay. So you do a chi-squared fit to what you predict to be the Higgs portal spectrum. The total spectrum is in blue. These are the primary contributions to it. You get a pretty specific mass and cross-section fit out of this fit, 40-ish GeV as promised, and about exactly a picobarn. So that's what you would expect. That gives you a very specific line signal because you know what the branching ratio is. So you can go look for the line signal.
Sorry, I have a question.
Yes,
Go.
please.
Previous slide, can go to previous slide. You see this is the mass you are considering is 36.7 GeV. Do you really need to go to fine tuning to the 0.1 GeV sensitivity? I mean, in other words, how the result the sensitivity to the mass of the dark matter?
Oh, good. So I will be looking for. So actually, this is just for illustration purposes. What this actually yields you is like a confidence ellipse in the parameter space of mass and cross section. I'll show you what the confidence ellipse
Okay,
is
sure.
in a couple slides, but it's not at the 0.1 level, it's like plus 5,
Plus,
plus minus 5 GeV.
okay, okay.
Thereabouts. Yeah.
Yeah. For this data, you have arrow bars, and then you have the shaded region. How do they represent the shaded? Is it just figures, sigma or something?
Oh, good. So the error bars are like those are Poissonian error bars. The shaded region is the difference between different, like those are the systematic variations. So the way they obtained this access was they fit the data to a bunch of different astrophysical templates, but these also have like internal models, like there are slightly different point source catalogs. There are slightly different models for the dark matter, for the galactic like diffuse emission, and then they also do a bunch of different other systematic variations. They changed the ROI a little bit from 40 to 30. They changed the energy range of their analysis, and for each of these they get like a slightly different access. So the shaded region is like varying over all of that. So statistical systematic. Good. Okay, we're going to actually do a line search. So all 14 years of data, as we promised, because this is a line search and we want like the finest energy resolution we can, we split the data essentially into 4 different quality quartiles of energy dispersion, and analyze each of them kind of independently and then stack them. Again, the ROI is essentially a 40 by 40. It's a round instead of square object, but whatever. This is a spectral analysis from 10 GeV to about 2 TeV. We go through it and we look for spikes essentially. This is the real world instead of this theoretical world, so we have to worry about things like PSF, which smears the reconstructed gamma ray in where you expect, like where it gets reconstructed on the sky, and the detector response is imperfect, so you measure a slightly different energy than the one that actually hits your detector. But these detector responses and PSFs are known, so we can convolve over them, which gives you a very specific prediction for like the amount of signal you expect for like your quality cut per annulus per energy bin for your model, and it's a pretty straightforward prediction. Your background, because this is essentially ostensibly a background-free analysis, is also pretty straightforward. We just model like the background to be a power law. You have a smooth thing, ostensibly you have a spike over it, that's the thing we're going to search for, and then we marginalize over like what this power law is allowed to be. The total expectation is the signal plus background, and then we do a Poissonian analysis for like essentially every mass. And we get something that looks like this. The black line is our like 95% upper limit, and the yellow and green regions are the 1 and 2 sigma containment to the 95% upper limit. If you compare with what 2015 Fermi is able to do with essentially functionally the same analysis, but with 7 years less data, we do at best like a factor of I think 5 better. And then in the high energy regions, we're subsumed by this more sensitive but only active at high energy experiment tests. So these are the constraints that we can place. Okay, and of course we find no gamma ray lines. I should have led with that. We find no gamma ray lines.
Can you go back? What does it mean when I guess I'm not understanding. Should I just ignore the lower panel because I'm confused by the exactly horizontal things there? there. Should I just ignore, can I just ignore that, or do I need to?
I mean, it depends on what you want. Okay, this exactly horizontal bit over here.
Yeah.
This is the region where, with like, for that energy bin, we just observe no counts.
But it doesn't seem to, why do you got all kinds of stuff going on the upper one? Aren't they on the same horizontal scale?
They are on the same horizontal scale. So like the test statistic being 0 doesn't like so this is the test statistic. So it's just how good the best fit is compared to the null hypothesis, right? And it being 0 is just that, like.
Oh, this is like the goodness of fit.
Yeah,
or
yeah, this
something.
is
like the goodness of fit, and since your model predicts nothing. I thought your model should predict. The best fit model is nothing, and that's perfectly in accord with your data, and that's what the horizontal line is.
Best fit model predicts.
You saw nothing, and your best fit model is there's no signal, and they perfectly agree.
Good. So this doesn't assume a particle physics model. We're just looking for any amount of line emission, and we find a best fit. Generally, that's something, because the null hypothesis is like no line, and then the best fit will generally give you some number. It's just like your best fit, like the non-null hypothesis model, which is like background plus line, has an extra parameter. Generally, the extra parameter will return you something. The question is whether or not that something is a much better fit to the data than the null hypothesis, which is just background, right? And
so what is square root of t?
yeah, so that's the difference in log likelihood with square root between the best fit, which is background plus signal, that we get, the lowest likelihood, with the same likelihood function but evaluated at like no line emission at all. That's the null hypothesis.
What does it look like if you had a gamma line? Suppose you do, what do we look
Good.
like?
So you would see like so anything that is above 2 is a 2 sigma detection essentially for a positive signal.
It's like 2 sigma locally. I mean, you have to
Exactly.
apply the look
Yes.
elsewhere effect.
Exactly. So this would be a 2 sigma local preference for a line. So just like at that energy, the model with the line is 2 sigma better than the model without a line. So the fact that there isn't any significant like fluctuation above 2 essentially is the statement that we find no lines. That's what the statement is. Yeah. And then you can place an upper limit in accordance. Good. Okay, so we find no lines. This is what we find no lines, no strong upward fluctuations. These are the limits that we can place. Okay, so we're going to take a look at what that means for the Higgs portal story, based on the fact that we have now these very specific predictions for what the total annihilation is and what the mass of this particle is. So these are the error ellipses I promised, with our results translated to a total annihilation cross-section. So in the Higgs portal parameter space of mass and cross-section, the GC wants this, and these are the constraints that we place. These are the two sigma upper bounds that we place.
I think the Higgs portal cannot explain the galaxy synthesis
Yes.
at 2 sigma level.
Yes, that's the pattern.
Okay.
And then we also rule out like sort of the Higgs portal thermal relic story below, I think, like 40 G, something like that.
But can you concoct models where the gamma has a cancellation in it?
Oh yeah, you can concoct models where the gamma has a cancellation in it. I think the easiest thing you do is just make your mediator a vector, and then you have a thing
Since
with three
massive
vectors.
vectors don't go to two massless vectors,
Yeah.
then you get zero that
Yeah.
way. Okay.
There are other cancellations that you can do, but that's the one I would start with. Okay, so this is what the Higgs portal story gives you. So let's look at like this is what I would call the empirically conservative story. So let's say your picture is literally the dark matter goes to a single type of fermion, B's or something like B's or taus. Or pick your favorite fermion. The dark matter only goes to that thing, and that one fermion spectrum is the thing that causes the GC. That also gives you a prediction for what the photon line is for, you know, like non-malicious mediators, and kind of it's more what you see is what you get, in that the thing that you get as annihilation final states are the only things that are allowed to run in the loops. The couplings are the same, so you're fully kind of independent of the blue part of the picture. This is not a particle physics model, as you might have noticed, but it's the empirically conservative statement. Let's assume that your annihilation is caused by this one thing. This one thing will give me a very specific and extremely suppressed gamma ray contribution. And I just wanted to show where that lies in the constraints that we can place. These are some very suppressed contributions. Most of these quarks, they're not very charged. You're suppressed by like that to the fourth. You know, like you're suppressed by alpha squared. You're suppressed by the mass ratio of like the final state to the initial state, which is typically a lot.
Sorry. First of all, this single annihilation, what's the mediator? Are you assuming? You stand more particle or new particle?
We assume that it's a new particle just because no standard model particle does this.
Okay.
But it actually doesn't matter what we assume as long as it's not a vector.
Okay. First of all, what about the mass that you are considering?
It actually doesn't matter.
It doesn't matter. Okay.
Because it entirely, like the thing that is mediator mass dependent is the same between the loop diagram and the tree diagram. So if you're just trying to find a ratio between like, how much gamma ray you expect per annihilation.
And the cancel. Okay.
Yeah, they cancel out.
Okay, got it.
So it's coupling independent. It's like mass, like mediator mass independent, and it's like the minimal assumption object. But the minimal assumption object gives you a very conservative prediction. So okay, you can essentially go through the story again, fit what you expect for the GCE, assuming only like chi-chi to tau, chi-chi to B, whatever, and then what this looks like in the line prediction. And it is indeed extremely suppressed. So we can't say clearly anything about these like single channel type of pictures.
They're completely excluded.
No, they're completely
allowed.
Oh, can you allow that? Sorry.
completely allowed.
Okay.
So like everything above.
I
large
put it wrong.
things are
Sorry.
excluded, Small things are allowed. Yeah. These are much beyond our reach.
Okay.
So yeah, so this is how far you would have to go to rule out these explanations.
Okay, got it.
So why is that so much worse? I don't quite understand why.
Because like for the Higgs portal, instead of the same thing in your final state being the thing that runs through the loops, this is like a top or a W. So you have
That gave you the big contribution to the Bourne issue.
yeah, exactly. And that's
Okay.
the thing that dominates.
Because
Like,
coupling.
you
You
have
call it
much
coupling.
larger couplings, and the masses like scale. it doesn't quite scale like this because this is no longer a small number.
Okay, so you have things that don't appear in the real radiation with much that appear in the gamma
Exactly.
with
The
much
thing that,
larger weights.
the things that run in the loop dominantly are things that don't appear, are kinematically forbidden to appear in annihilation. So, for the Higgs model, that gets to help us,
So
and it
how-
makes a large difference.
To account for the access, do you always need the dark matter to be in the few tens of GeV? Is that the
I mean, kind of, yeah, because most of, essentially, for a heavier dark matter, you just move the spectrum in this direction. And the spectrum does peak at like a couple of GeV. And you basically see nothing here. Like the statistical error bars are going to zero. Like this is like 1 photon each, essentially. So yeah, it would be hard for a heavier thing to explain this.
Then you can consider Z portal.
Yeah.
Have you tried the Z portal?
A what portal?
A Z boson.
A Z boson. It'd be a massive guy. You don't get any lines.
Z doesn't go
Sorry,
together.
it would be
Okay,
like a vector loop with like,
of Gabor copy.
yeah.
Because they does not go to gamma gamma.
Yeah,
But yeah, yeah.
So this just wouldn't be a good strategy for
Yeah.
that.
But could you do it at gamma Z?
Okay.
You could go to gamma Z.
I mean, it's monochromatic line again.
Yeah, yeah.
You could go to gamma Z, but your dark matter would be a little kinematically suppressed because you do want like a 40-ish GeV dark matter. So you could push it to like 45, but then you'd get, or like you're at the kinematic edge for like gamma
Okay,
Z.
gamma Z star.
Yeah,
But
exactly.
maybe it would be too weak then because you're too far off the Z.
Yeah, like so if you're far off the Z, you lose the monochromaticness. Yeah.
Right, yeah, definitely.
So not, yeah, so we're open to other, yeah. Ultimately, this is a very general object. Give me a model, and I can tell you where it lies. So always open to other models looking for that. Good. Okay. So after taking a lot of time, I'm going to summarize this bit quicker. We've gone through kind of the weeds that I wanted to talk about, so hopefully this won't take very long. And you've heard most of the story. Okay, so this is a search on the gamma ray continuum for the Higgsino. So the Higgsino is one of these like certified old-fashioned WIMP TMs. This is a bit where I pick up the theory prior and assert that of all the WIMPs, these are the nicest ones that we would want. As a dark matter candidate, obviously the SUSY neutralinos are very, very well motivated, and at least in this idyllic picture, they're extremely predictive. The number of free parameters are relatively few, especially in the sort of nearly pure cases. You essentially just have masses, your couplings are fixed, and you kind of, know what you will get. In this nearly pure separated picture, nearly pure Bino is extremely ruled out by Fermi bounds, by direct detection, and nearly pure Reno is quite ruled out by indirect detection. Essentially, the story there is that a nearly pure Reno, at least in thermal expectation, if you want a nearly pure Reno and a thermal picture, and that to be 100% of dark matter, you end up with like a 3TeV object, and that object is pretty sensitive to somersault enhancement, so you get some very enhanced late universe annihilation in the halo, to the point that is pretty ruled out by the amount of gamma rays that we observe, unless we do weird things to the dark matter. That's the Reno story. But the nearly pure Higgsino is actually real hard to rule out.
I think just to make sure I'm remembering back when the pure Beano case, I thought there was you're talking about a very heavy Beano, right? If it's around the fermion masses, I thought it was still fine. I thought that was kind of a nightmare scenario that's very hard to rule out.
You're talking like a 100 GeV or like?
Yeah, really close to that, but then somehow the fermions are, if the Beano is just a bit lighter than the fermions, and the fermions don't decay with a lot of missing energy, they're hard to see, they're not have a big rate. I thought that was okay. I don't want to derail your talk. I just wondered if you happen to know.
That's a.
I'm not sure. I don't want to.
100% sure.
Okay, it's okay. It's not.
It's Beano needs to be quite light. Right?
Yeah,
That's
it's
why
light.
it's ruled out by fermion.
Yeah, but I thought that there was always a story that if they were kind of degenerate, then say the fermions decay. It's a little bit of a conspiracy story, but I thought that was kind of a very difficult thing to rule out.
It is.
But I don't know. I haven't paid attention.
It is possible that you can play these kinematic games and kind of like.
Yeah. Okay. Anyway, it's fine. I don't want to
I'm
derail
not
your
sure.
talk.
Yeah.
Okay.
I believe it is difficult, but again, I'm not sure it's difficult. Okay, the talk is about a hit scenario. They're actually pretty hard to roll out. So the same expectation as the Wino, like thermal picture, 100% of dark matter gives you like exactly like 1.1 TeV. That's the one parameter that you have, and you kind of lock it in with the omega dark matter is 0.12 degree of freedom. So in this minimal picture, you have some dark matter and some neutral state and some charged state, 2 Majorana degrees of freedom, one charged object, and they're roughly the same mass with some small mass gaps that are allowed. This charged mass gap is like radiatively lower bounded at like 350 MeV. This object, the mass gap between the dark matter and like the other neutral degree of freedom is ostensibly allowed to be 0, but essentially, depending on how heavy the other neutralinos are, is allowed to be a thing. And it's in fact quite necessary that it is a thing. So for annihilation, we want about 1.1 TeV mass. So that actually fixes that quite firmly. For elastic scattering, the thing that kills WIMPs, as long as this mass gap is above like about 200 keV, you essentially make it so that direct detection can almost never see this object. You just make this heavy enough that you don't have enough kinematic energy to like upscatter into the heavier state. These are Majoranas. They don't couple to the Z's by themselves. So this is kind of the only thing you can get. 200 keV is all you need on a 1.1 TeV object to totally saturate the direct detection bands. Okay, so, and like 200 keV is nothing in the indirect detection world. That'll make like 0 difference. So we want to be like kind of dramatic about it. This is kind of like the last bastion of like traditional MSSM dark matter. If we can say something definitive about it in the next 5 years, obviously we find it, it'll be huge. If we don't find it, that actually does say something quite strong about the nature of the universe. So I think it's important that we keep this in the back of our minds, that this is a thing that is compelling. It's still compelling. We haven't been able to find it for so long that sometimes we forget that it's still there, but it's still here. We'll try to look for it. Okay, so the story is quite the same as it was before. We're looking for a continuum signal, so the same type of story that I told for the thing that produces the galactic center axis applies, albeit at a much different energy. I'm going to say some slightly different words about the amount of dark matter and the annihilation cross-section in the next couple of minutes. I promise I'll try to wrap up soon. Okay, the fiducial model, we set the neutral mass gap to like 200 keV, the thing that saturates the direct detection band, and the charged mass gap at like 350 MeV. When I said the annihilation was dominantly set by this is kind of a lie. There is still a little bit of somersault enhancement, and though it is not a very strong effect, but we still take it into account. This means that the final states are these objects. There's like a Z gamma allowance. You compute the somersault enhancement in the normal way, solve the Schrodinger equation, you do the thing. And the continuum contribution that we're looking for is like this stuff plus 1/2 of this stuff. You might notice that we also produce a monochromatic line. This is a very prominent signal for the Higgsino as a whole. This is a pretty large Rankin ratio that you expect for a gamma ray line. And so this is...
you have gamma Z.
Huh?
Sorry, you have gamma Z there.
Yeah.
This will contribute to a line, right?
What?
The gamma Z will contribute to a line.
Yeah.
Okay.
Yeah, you have gamma Z, so like the line contribution is a gamma gamma.
But
plus-
now she's talking about something at 1 TeV.
Yeah.
Before we were talking about something
At
at
G.
40 G.
That's a totally different
40
story.
G,
Yeah,
the
totally
was
different.
off shelf.
Totally different story.
You're
Okay.
not sitting on resonance there, and
Yeah.
those two lines are very close to each other, right?
Yeah, exactly. At one TeV, like a 90 GeV is basically an aspect.
Oh, you're looking for, okay.
Yeah. So essentially, it just like you get like 1/2 of this is like still a monochromatic line. Like
But now are we just saying that GCE is astrophysics, or
this is a totally different energy range.
Yeah.
So yeah, this is an entirely independent from GCE.
Okay.
Yeah,
so
I mean like.
got it.
this half of the talk, the GCE is pulsars.
Well, in this half of the talk, the GCE doesn't have to be dark matter. Yeah, exactly.
Okay.
Like, I'm not even
Well,
claiming
if it
that.
is dark matter, then you have to change your abundance of these
That's-
guys.
Yeah.
That's certainly true. It's certainly true. I think in the first
She's
half of
also
the talk.
not solving the cosmological constant problem.
Yeah, one thing at a time.
Yeah.
I think in the first half of the talk, GC doesn't have to be dark matter, but if you think it is, then there are consequences. In this case, I'm not beholden to any of that.
But
Okay.
you do have to know whether the GCE is dark matter,
Yeah.
because it changes what mass you want here,
Yeah,
because that's set by the abundance of this part of dark matter.
that's true. Right now, we're assuming the Higgsino is all of dark matter,
Okay.
and it does not produce a GCE.
Okay.
Good, but it does produce a line, like a TeV.
Yeah.
And people do search for this line. The Hess experiment has the strongest constraints on that, and that is the strongest constraints on the Higgsino that we have. It's not quite at prediction yet. We're going to try to do a little bit better.
Okay. I think the second half of the talk is saying you're trying to put a constraint on the Higgsino. There's no exercise, right?
Yeah.
That's a
There are no
claim.
excesses.
Yeah, okay.
There are no excesses. There's just gamma ray data. In fact, we're going to like start analyzing 10 GeV and up. So we're not even analyzing the excess bit. It's just the high energy bit of the Fermi data, where this annihilation signal is expected to show up. Yeah, this is not a GC axis story at all. Good. Okay. Okay. One quick note on the Haley profiles, because again I'm no longer beholden to the galactic center axis. I can ask myself if NFWs are really our best guess for dark matter distribution in the universe. We know that baryons do exist, and we recently found out that they're pretty important to the distribution of dark matter in the center of the galaxies. And we have now some like fairly sophisticated simulations that can give us some degree of prediction for what this distribution would look like under the influence of baryonic physics. They're at least a better ansatz than the NFWs that we have used of many years. So this is a suite of like 12 Milky Way-like hydrosims, 6 of which were even involved in pairs to simulate the Milky Way Andromeda dynamic. They're named in pairs: Romeo, Juliet, Thelma, Louise. And these are the highest resolution simulations in the game, which is why we use them. It's very important when you're trying to resolve J factors in the center of the universe, center of the galaxy. Okay, so this is what the continuum spectrum you would expect for a 1.1 TeV Xena would be. It's like the gamma ray spectrum, flux. And this is the amount of uncertainty that is introduced by varying over these 12 different hydrodynamic simulation phases, with this bolded one being the NFW. So you can see that this actually gives us a lot of freedom for what we expect.
So now question, why is this so broad?
Why is this so?
This is not, am I just, maybe I'm just zoned out here or something, but we're talking about photons?
Yes.
Or just, so why isn't this is the spectrum? So why is it so broad? Why is it going all the way down to?
You mean why the continuum to the?
Because it all comes from pi zeros, and there's a big distribution in the energy of pi zeros coming out of jets, I think.
So this is, so I thought the solid line is not just the signal, it's signal plus background then?
No, all of this is signal. The signal
Yeah, this is
like,
signal.
yeah, dark matter annihilates to like W's, and then the W's like,
Oh, sorry,
radiate.
okay, yeah. So this,
I think
sorry,
that
so
bump
that's
on the right is
this
probably the radiative decay, where you have a
Yeah,
real photon
okay.
radiated off.
So these are cascade.
And that's real, but everything else is probably pi zeros.
Sorry, I was back in the first half of the talk when we were talking about.
yeah, I did transition a little bit.
No,
I
I
should-
should
I
have
should.
followed you, I didn't, thank you.
And this is a full continuum signal. This is
Yeah.
the big non-suppressed object.
Hmm.
We're looking for the easy guy now. Okay, and then just to mention this like little hatched region is if I vary the mass gap between the various Higgsino states from like the fiducial, it's like 200 keV to like a couple GeV, 2 GeV. This is roughly the amount of uncertainty is very much the halo profiles. And the the difference in the fiducial model and mass gaps really doesn't make a difference. The secondary contribution wasn't much smaller.
I'm just a little confused. I mean, so at each, in principle, it seems like the dark matter profile is telling you the intensity of the source at a given location. But the spectrum is just, well, these are just some big, heavy dudes at rest. They're decaying in exactly the same way everywhere. And so I'm just wondering, do you really have a huge uncertainty? Can't you somehow use that to, get rid of the uncertainty? I mean, it's true that sort of point by point you don't know the intensity. But it seems like isn't that by far the dominant effect of you not knowing the dark matter profile? Still the same spectrum everywhere I look.
Sure. I think this would be true if I had a detection of dark matter
I see,
annihilation.
right.
I could fit that to a dark matter profile.
Oh, you're telling me you
what-
haven't detected dark matter.
I in fact have not.
Okay, no,
I
I
in
see,
fact
you're
have
right,
not.
you're right. The point is you
There
don't know what
There
bound
would
is
still be a
that.
trade-off between J squared, or the astrophysical stuff, and the annihilation
Yeah.
cross-section, right?
Yeah, there
It's
certainly,
like totally degenerate with each other.
Yeah, there certainly would be, but I would also be able to give you a fit on like what I would like what the like if I detected something, what that detection prefers as spatial variation. But right now, if I'm trying to place constraints on a signal that I don't see, then the strength of the
You can't do something like, if I integrate over some region, maybe can I try to claim that even if I don't know, exactly where the dark matter is, I know something about the total amount of dark matter in there, like I can see stuff orbiting around it, so I can infer some total amount of dark matter. Maybe you can't do that.
You can see stuff orbiting around it. So you can
Well, like, I guess, I mean, this is our galaxy, right? This is the Milky Way.
yes, indeed.
Maybe I don't know how fast things are rotating around the outside of the Milky Way, maybe. Okay.
I mean, we do have a decent idea of like, how to say this. We do have a decent idea of like from rotation curves measuring like
Yeah.
rotation velocities.
Because I mean,
of
you
stars.
know, because I could imagine that this is at least just about an order of magnitude uncertainty there, right, in that upper thing. And so I could believe that if I point there and I ask you how much dark matter is there, I could believe there's a factor of 10 uncertainty. But if you're integrating over some large region, wouldn't the uncertainty be smaller in the total amount? And since you're just adding up the
Okay, I'm going to say
events?
a couple things. So all of these profiles are normalized so that they give the same density at Earth radius. So
Oh,
they,
okay.
um,
So even then, it's a factor of 10.
yeah. So
You're
like
right.
they're
Okay.
they're roughly this amount different.
All
Yes.
right.
Yeah. So they are normalized to like kind of the one increment we have, which is the local density.
Okay.
Um,
I guess, oh, I see, but I guess somehow they can be more or less cuspy, and that can really affect the signal a lot, because
Yeah.
it
I
goes,
mean,
the
I think
signal goes like
maybe the
the
thing to keep in
square of the density, right?
Exactly. Ultimately, the region that we are searching over is a very small region compared to like our
Right, I
distance
see,
from
right.
the center of the galaxy.
Okay.
So
And it's a region where there are a lot of baryons. So
There are a
whereas
lot of
dark matter
baryons.
dominates in the burbs where we are, there's a lot of baryons in there in the center, right? Isn't that
yeah,
true?
there are indeed a lot of baryons in the center. So I don't know. Yeah, there's a lot of uncertainty. In the, yeah, but there's also a lot of dark matter. That's not really where you expect the dark matter signal to be. So you just have to live with it and then find it or not find it.
Sorry.
So,
For the WWZ curve, they are assumed to be in the NFW profile. It's just a component coming from the WWZ, or
yeah, absolutely. So yeah, this is just the breakdown that
Okay.
goes into this total. I just wanted to show what the shapes are. Yeah. Okay. How much time do I have?
You officially have no time, but you will continue 5 minutes.
We're gonna wrap it, please.
Yeah, I'm gonna be really fast. Okay, so we do a search. We do a search at 10 degrees. We mask the galactic plane. We mask all the point sources we know about. It's a spectral search. The background fitting is a little bit more complicated because like there's actual background now. So we have like these diffuse galactic emission templates, some point source spectral templates, and some isotropic emission. They add up. So if the actual data looks like this, these are various background components and our signal example. So we're very much dominated by the diffuse background. This is kind of the signal magnitude in comparison to the data. Good. A bunch of details. The point is, ultimately, we find no Higgsinodes. This is our best fit line, not the upper. This is our best fit line, and then the 1 and 2 sigma containment across our best fit. So this red line is like the thermal 1.1 TeV. And this red line is what you would expect for an MSSM Higgsino. Our constraint is far above that, so we cannot rule it out. And we do kind of comparably to what the Hess line search can do. They do better at higher masses. We do better at lower masses. That's what we can say. Good. We find no Higgsinodes asterisk. The asterisk is that depending on what halo profile you look at, so this is for the NFW, which is the thing that we can compare the Hess results against, because that's what they assumed. But if we take a little bit of a more sophisticated guess for the halo profile, we do get like some upward fluctuation for the Higgsino at roughly this like 1 TeV mass scale. It's a 2 sigma upwards fluctuation. Take that at face value. For this Higgsino search. So that is our constraints are weaker. There's a 2 sigma upwards fluctuation at about 1 TeV. Those are the sentences that I'm comfortable saying. You can do some variations on this analysis, assuming like a subfraction of dark matter that weakens your signals, blows up your constraints. Whatever. These are some extended results. I'm going to breeze past these.
Do some people look at dwarf, galaxies
Yeah,
and
people
stack them up and stuff? And could
people
you-
have done that. I don't know if they've done that for the Higgsino lately, but it's definitely on the list of things to do next. Good. Okay. Quick conclusion. Sorry for going over time. Indirect detection is still like one of the best ways to test a certain type of idea. The classic WIMP paradigm has its stance, and there are still very compelling things that have been around for a real long time that we haven't gotten closure on, including the galactic center axis, including some very compelling models that are difficult to look for elsewhere, like the Higgsino. And this is a sampling of the type of physics that we can look for with this program. And we're kind of at the changing of the guard with regard to like these indirect detection programs. Fermi is kind of chugging along, but unclear for how much longer. And there are these new experiments coming to take its place, mostly at higher energies, heard in CTA, kind of with the largest overlap with Fermi, but really nothing at the tens of GeV range where you would really want to get closure on some of these GC adjacent ideas. So it's worth paying attention to these upcoming experiments, but also worth thinking about getting something that really covers this range. Okay. Thank you.
Any more questions?
So I'm not in the field, but in your presentation, there's always this sigma times v. Why are we interested in the cross-section times the velocity instead of just the cross-section itself?
Because you have a distribution of dark matter, right? You have a distribution of dark matter, and each of it has like a different velocity from the distribution, and you want like the quantity you are interested in is the like average amount of annihilation you get, averaged over this entire velocity distribution.
If velocity is 0, dark matter will see it, it will not collide. We need dark matter to annihilate it, to create a signal. Yeah, we need dark matter to collide with each other. That's the velocity. If velocity is 0, dark matter just sit here, they don't talk to each other. There's no annihilation. Yeah.
The mean free path of a dark matter going through other dark matter depends on its velocity and depends on how much other stuff there is.
Any more?
What is this HERO instrument? I know about CTA.
It's a herd, actually.
Heard, sorry.
Yeah, they look a little similar. I see it.
Yeah.
It's this like Chinese gamma ray satellite. I don't quite know what stage it's at, but
Okay.
it's a thing that.
It's able, even though it's a satellite, it's able to go to much higher energy.
Yeah.
Usually the fluxes drop, and that's why, Fermi peters out
Yeah.
in higher energies. Wonder how that one works.
I don't fully know. I haven't gotten a lot of documentation on it. But-
Maybe it doesn't look at direct gamma rays. Maybe it looks down and looks at. Is it possible that it looks for showers? So it's not just limited to its own collection area.
I be surprised. So the one thing I know about her is that it has really good energy resolution.
Okay, well, that's probably inconsistent with
Yeah,
what you
yeah,
said.
so I don't think that's what it does, but I don't know for a fact. The thing that I know is that it has really good energy resolution. That's the main thing.
Okay. So if there's no question, let's thank the speaker again.